Welcome to the Walton Pi. Today we're going to go through some examples of showing functions are continuous. Let's suppose that f of x is defined piecewise as 2x if x is less than 3, 7 if x is equal to 3, and x squared if x is greater than 3. A question we might ask ourselves is, where is f continuous? So we have a couple theorems that we talked about in the last video. So a function is continuous if it is differentiable at that point. So places where it's differentiable, 2x is a differentiable function and x squared is a differentiable function. So those two functions tell us that as long as our function is behaving like one of those, it is going to be continuous. So from the 2x, that tells us it is continuous on the interval from negative infinity to 3. And then the x squared, it's going to be continuous from 3 to infinity. The only thing we have to question ourselves about is, what about 3? So at 3, is it going to be continuous? So to check if it's continuous, that means that the limit as x approaches our point, so as x approaches 3 of f of x, it first has to, 1, it has to exist, and 2, it has to be equal to f of 3. So if we look to see, does the limit as x approaches 3, is that valid? If we look at the limit as x approaches 3 from the left of f of x, this is going to be equal to 2 times 3, or 6. So it's approaching, so our graph is looking something like, we have 2x, and so right here is a value of 6. Then we know on the other side, so the limit as x approaches 3 from the right of f of x, well, this is going to be 3 squared, which is 9. So it's coming down and doing something like this, and it's approaching 9. So first off, the limit doesn't even exist. So it fails to exist at that point. Now, if we had changed this function, so instead of being 2x, it had been 3x, then this 2 there is going to be a 3, so that is going to be going to 9. And so now the limit does exist. So we would need to fix our line here. It would be doing something like that. Now the question is it continuous at 3 still? So the limit exists, but f of 3 is 7, which is not the same as 9. So our function is looking something like this, and so we can see from the graph this is not continuous. However, if we were to change this function a little bit more and make that a 9, now that function is going to be continuous everywhere. But that's how we would be able to check this sort of thing. Let's do one more problem. Let's check to see if we have f of x equals 13x minus 4 if x is less than 2. We got 11x from 2 to 8, and then let's say we have x plus 80. We want to see, where is f of x continuous? So again, from each of these different pieces, we know, this is from x bigger than 8. So for each of these pieces, we know that these are going to be continuous on each piece because each of the functions is continuous on those pieces because they're all different polynomials. So we know it's continuous from negative infinity to 2, from 2 to 8, and from 8 to infinity. Notice that even though the bounds on this are inclusive. Our interval is the open interval. It does not include the endpoints because it's only continuous if the limit is equal to the value of the function from both sides. So that means we need to check what is the limit as x goes to 2 and the limit as x goes to 8. We need to check both of those limits. So if we look at the limit as x goes to 2 of f of x, we have to check the two different sides of the limit. So we are going to actually have to do two different one-sided limits. So the limit as x goes to 2 from the left of f of x, that is just going to be the limit as x goes to 2 from the left of 13x minus 4, because that is what the function is to the left of 2. So if we evaluate that, that's going to be 26 minus 4, which is 22. Awesome. If we then look at the limit as x goes to 2 from the right of f of x, well, that's going to be the limit as x goes to 2 from the right of 11x, which in this case is also 22. So this limit is the same from both sides. So that means the limit of this is equal to 22, and now we are checking, is that equal to f of 2? Well, f of 2 is going to be 11 times 2, which is 22. Yes. So that means it is continuous at 2 as well. What we can then do is we would then need to look at what about the limit as x approaches 8. So we have the limit as x goes to 8. So we have the limit as x goes to 8 from the left of f of x, which in this case is going to be the limit as x goes to 8 from the left of 11x. So that's going to be 88. And we check, is that equal to the limit as x goes to 8 from the right? So that's going to be the limit as x goes to 8 from the right of x plus 80, which is going to be also equal to 88. So those two are the same. So now we just have to check, what is f of 8? Well, f of 8 is going to be 11 times 8, which is 88. Everything matches, so it's also continuous at 8 as well. So that means f is continuous everywhere. So that is how we would go about checking if a function is continuous and how we would be able to check it. You just check, does the limit exist, and is it equal to the value of the function at that point? If both of those are satisfied, then the function is going to be continuous. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.